All right, good afternoon, Dr. Pinchbeck. Zach is back one more time with another one of my student videos. This is the last one for the semester. And I've written down the scenario that you've written down in Brightspace, so I know I'm on the right track. It reads, you are designing a holiday cookie tin in the shape of a cylinder. The circular top and bottom of the tin are made from thicker material that costs 10 cents per square inch. The thinner side material only costs 5 cents per square inch. You want the capacity of the tin to be 250 cubic inches. What dimension should you use to minimize the cost of each cookie tin? Now, before we start, I want to clarify that I had previously done the math the previous day because it took me a while to do the math, and I felt that just doing it while recording this video would just ruin the pacing drastically. So, let's start. You are designing a holiday cookie tin in the shape of a cylinder. All right, so we know the shape. It is a cylinder. You want the capacity of the tin to be 250 cubic inches. So that is the volume of the cylinder that we want to construct. Now, the formula for the volume of the cylinder I have right here is volume equals pi r squared times the height. Both the radius and the height are greater than 0. You want the capacity of the tin to be 250 cubic inches. So we have our volume. So pi r squared h equals 250. What dimension should you use to minimize the cost of each cookie tin? Since we have radius and height, we will calculate those as our dimensions. So now here we have pi r squared h equals 250. Well, we can figure out how to calculate the height, which I've done right here. All we have to do is divide 250 by pi r squared. And this will be h of r. And to just show that, I have multiplied pi r squared by the height, which is 250 over pi r squared, and that equals 250, basically because the pi r squareds cancel out. Now, to get back, the circular top and bottom of the tin are made from a thicker material that costs 10 cents per square inch. The thinner side material only costs 5 cents per square inch. So in that case, we're not talking about volume, we are talking about surface area. Now, to calculate the surface area, we have to take the area of the two bases, or the two circles, so that is 2 times pi radius squared, so that covers both circles, plus the area of the rectangle in between the two circles, which is the circumference of a circle 2 pi r times the height of the cylinder. And we've already established before that 250 over pi r squared is the height of our cylinder. So we will substitute that in for h. And when we solve that, we can distinguish that as 500 pi r over pi r squared. And since both the numerator and denominator share a pi r in common, we can simplify this as 500 over r. So the surface area of the cylinder in entire terms of r is 2 pi r squared plus 500 over r. Now let's get back to the pricing. The circular top and bottom of the tin are made from a thicker material that costs 10 cents per square inch, whereas the thinner side costs 5 cents. So all we have to do is multiply each terms of our surface area by those products. So we multiply 2 pi r squared by 10, because it costs 10 cents for each circle, and 500 over r by 5 cents, since that's what the area costs. And we are left with the cost in terms of radius is 200 pi r squared plus 2500 over r. And I redid this as 20 pi r squared plus 250 r to the negative first. And there's a set reason for that. So this is our cost function, and we want this to be a minimized cost. So we have to figure out what exactly the length of the radius should be in order to minimize the cost. So we'd have to find a critical value in this case. critical value for a function is a value in which the derivative of the function will equal 0. So we take the derivative of the cost function, which is 40 pi r, which is the derivative of 20 pi r squared, and add that by the product of -1, because -1 goes out in front, times 2500 r to the -2, because we take the exponent that is 1 less than that. And we can simplify this as 40 pi r over 2500 over r squared. Now, like I said, the critical value is the value in which the derivative equals 0. So we set the derivative of the function equal to 0. So 40 pi r minus 2500 over pi r squared equals 0. And when two terms equal 0, when the difference of two terms equals 0, that means that they are equal to each other. So we can rewrite this as 40 pi r equals 2500 over pi r squared. And to get rid of the fraction on the bottom, we can multiply both sides by r squared. So we are left with 40 pi r cubed equals 2500. We're off to a good start. But in order to figure out r, first we have to have the coefficient of r equal 1. And we have a 40 pi over the r cubed. So we divide both sides by 40 pi. So we're left with r cubed equals 2500 over 40 pi, which can be simplified as 125 over 2 pi. And since it's r cubed, we can take the cubic root, yes, the cubic root of 125 over 2 pi. Functions that have a term that has an exponent of an odd number will always have one solution to it. So r equals the cubic root of 125 over 2 pi, or approximately 2.71. So that is our critical value. And so we're going to take the critical value here and plug it back into our cost function and compare it among some other points. So I've done this math already. The C of 2.71 equals up to 1,384 cents or $13.84. Compare that to the function of 2.5, which equals 1393, and 2.9, which equals 1391. These R values are different than 2.71, which is in between them, and yet they are more expensive than the cost of 2.71. So we can conclude that C of 2.71 is less than C of 2.79, which is less than C of 2.5. So that concludes the minimal cost of each cookie tin. So now we have the radius, which is 2.71. Excellent. Now, all we have to do now is figure out the height. We have the radius, and now we need to figure out the height. So we plug 2.71 back into the HR function, and we get 250 divided by pi times 2.71 squared, and we get approximately 10.84. Now, to conclude, we have to figure out whether or not we can plug those back into the volume function and get 250. So pi times 2.71 squared multiplied by 10.84 does approximate to 250. So in the end, to minimize the cost, each cylinder has to have, for dimensions, has to have a radius of 2.71 inches and a height of 10.84 inches. So that's our answer. It has been an honor doing this video, and I will see you in January.